Good day, my name is Professor Oyaladipo. I'm to demonstrate to you what you are to do in experiment 13. The title of that experiment is determination of the focal length of a concave lens. A concave lens, unlike a convex lens, will produce a virtual image which we cannot cast on a screen. So we need to devise a method to determine its focal length. And we have two methods for this experiment. The first one is the use of a concave mirror. A concave mirror will form an image the same side as the object, and the image is going to be upright just like the object. So we want to use a concave lens to create more or less a virtual image that will now serve as object to our concave lens. Okay, that concave lens, then we can make some measurements for us to allow us to determine the focal length of the lens. So we start by this. I have a concave lens that we want to determine its focal length. I have a concave mirror, and then I have a convex lens for the second part of the experiment, and I have the object this way. Now, what we are to do is to mount the concave mirror just like I have it now on this optical bench, and then introduce the object, the pin in front of it. Now I need to adjust this object until the inverted image that I will see from this mirror, when there is no parallel between that image and the object. And I want to record that position because it's very, very important. Now, if I look this way through the lens, I can see an inverted image. Then I need to adjust, if I need to move the object far away or towards for you to be able to see the image that we are looking for. The moment you can see the image, the next thing is for you to look for a point where there is no parallax between that image and the object. I can see the image. If I move the object away from the mirror, it appears to me as if the image is going towards, away from the object. Now I move it closer, and I can see that that image is actually coming out. Definitely there should be a point at which the image will be directly on top of this object, and that's the location that I'm looking for. So I keep adjusting, and then it's by method of not parallel between the image and the object. So I keep adjusting, and I have this position at which there is no parallel between the image and the object. So I mark this point as point C, and that C throughout the experiment is fixed. I ensure that I don't change the position of the lens as well. So that is to be recorded. So I've done that. You have to record that as position C. Now the next thing is to introduce a concave lens in between this position and the mirror. Let me try and do that now. So, and ensure that for this experiment, the position of this lens will not go beyond C. So I have this value this way. Now I need to take this far away because the image I can see now is just an upright image. So I need to move this far away. Okay. And now I can see more or less an inverted image. So I need to adjust this until there is no parallel between this object and the image. So I'm moving this closer to the lens, and the position of no parallels between the two is somewhere here. So don't forget I've noted the position that I call C, and this is now C prime. The position of the lens is N. So I have 3 points now. I can draw the diagram here to show what we're talking about. That this is the lens, this is the mirror, so to say. Okay. I have the lens somewhere here. And I'm talking because don't forget I've already marked the point that I call C, and there is a point C prime. That is the last position I've just recorded, in which I have the inverted image directly on top of the object. This is the image. So this is C. So, and the position of the lens is N. So I need to recall these 3 points. This is C prime. So I may have my table to look like this. I have N, I have C, and then I have C prime. And then from there, I can determine this value. I can determine U. I will tell you how to do that. I can also determine V. So the distance between C, N, and C prime is actually U, N minus N. Let's just call it NC. NC is the object distance, then NC prime is the image distance. So that the moment I have this, for the first set of values, I can directly calculate U and V, and then I can also calculate 1 over U, and then 1 over V. Please remember that for this arrangement, U is positive, and then V is negative. So the way we now change the position of N, so to say, to maybe 4, 5, 6 different points, and we ensure that that point will not go beyond the point that we have recorded as N, so that we can have like 5, 7 set of values. And then when that one is done, from this well-known formula 1 over F, that is equal to 1 over V plus 1 over U, we know we have calculated in the table 1 over U, we have calculated 1 over V. Then we can plot a graph. We can rearrange this equation in such a way that, don't forget, V is negative, U is positive. So what I've done is we can move this to the other side, and we have this equation that we can compare with the general formula, the equation for a straight line, that is y that is equal to mx plus c. So a graph of 1 over u against 1 over v, we have a slope of 1 and intercept of 1 over f. So meaning that the intercept c is equal to 1 over f. And from that we can calculate the focal length of this particular lens. Now the second method now that we are going to use is the use of a convex lens. A convex lens, I have a convex lens here, can form different types of images depending on the position of the object from the lens. When the object is placed between the focal length and the lens, we expect to have an erect and magnified image, which is going to be formed the same side as the object. But for this experiment, we don't want that kind of image. We want an image that is going to be formed at the other side of the lens. So I will ensure that I place this lens. This is the object. I ensure that the object is actually placed beyond the focal points. By that, image is going to be formed to this side, and that image is going to be inverted. That image is now what I want to locate using another pen. For the first experiment, we just use one pen. The image object pen is still the search pen. For this, we need another pen that I call the search pen. This is the image. This is the search pen. If I look through the lens, I can see an inverted image, and it's actually to this side. So I want to locate the position of that image. So I want to move this to where the image is. And to me, the image is somewhere here. So this position is now, I'm to note it and record it as C, just like the first experiment. Now what I need to do is I need to introduce a concave lens in between the lens and position C, and then look for the new position of this image, the new image that is going to be formed. So I've introduced a diverging lens, a concave lens in between the convex lens and C. Now I need to look for the new position of this object, which I want to see the image first before I start looking for it. Okay. Yes. I'm looking for that image. The moment I can see it, then I start searching for it. Oh, it's actually really big. Yes, I can see it now, but it's really big. So I'm searching for that. And what I need to do is just to use the method of ensure that there's no parallel between that image and the object. And I have it somewhere here. So this position becomes my C prime. So I have 3 points now. The position of the concave lens is N. Don't forget the first position that we determined is actually C, and this is C prime. And what I need to do, just like we did for the first experiment with the method of concave mirror, is to change the position of N to 5-6 different points. Ensure that I don't go beyond point C, and then come back and use this same formula that we have used for that. For this arrangement, is going to look like this. I have a concave lens to this side. I have the object that I have to this side, that I call the object. And then the image is formed. I've located point C, and then the C prime. Now this is still N. Then I need to measure what I call now the object distance, that is U, and then the image distance, that is V. So object distance is Cn, image distance is C prime N, or NC prime. But for this experiment, object distance is negative, image distance is positive. And then we come back to this formula that we know. After we might have done the calculation as to determining the object distance, the image distance, and we have calculated 1/V and then 1/U. We can come back to this equation and rearrange just the way we did for the other one. Don't forget, for this, we are saying that U is negative, meaning that we can rearrange in such a way that we have this equation to look like this. I can have 1/V that is equal to 1/U plus 1/F. And what I've done in this case is to move 1/U to the other side. So I can then plot a graph of 1/V against 1/U. And when I compare this with the equation of a straight line, then the intercept is still 1/f. So from that intercept, I can determine the focal length of the lens. Then the next thing to do is just to compare the two values. The focal length will determine from the method of concave mirror, the focal length that will determine from the method of a convex mirror. And then it is not expected that there will be a large difference between the two values. That is what we are expected to do in this experiment. So I want to believe that you can go into the lab, perform the experiment, do proper recording, do your calculation, and then submit your report. Thank you.